But I'm very happy to have Fedele Lizzi here to talk to us today about pointless physics.
Yeah, well,
Pun intended.
yes. Well, okay, the real title could have been non-commutative geometry, but, actually the pointless physics is inner pan on von Neumann that talked of pointless mathematics. So what I will do is we'll talk, hopefully will be a couple of Einsteins in your ratings, although by definition I think it will be a relative statement how many Einsteins it is. And I will talk about how the concept of points, as we grew up knowing, it's probably untenable in quantum gravity. So this is the thing, but I will get there. And I will start from afar, from about a little less than 6 years ago in my elementary school. And I said, I don't have the book anymore, but I remember that there was a definition of a point. And this was the first definition in geometry that was encountered, probably the first definition in elementary school. And it was saying a geometrical entity without a dimension. And I couldn't understand what it meant, but I couldn't understand why there was a need of defining things. I was 5, 6 years old. And so I didn't know what it meant, but I knew what a point was. Because, you know, you do it with, and I knew that, of course, I needed to sharpen my pencil first, because then otherwise it wouldn't be a good point. Okay, going to more serious authoritative things. First, Euclid. Euclid defines point as that which has no part. And even higher authority than Euclid is Wikipedia. I cannot think of anything higher than that. And it's a primitive notion upon which the geometry is built, which is exactly what my elementary school was saying. It's something that is there that we cannot define because we know what it is. And so let me get to the point. Let me try to see how in physics we use points. And in mathematics, of course, there will be different definitions coming from set theory, but in physics we use points. And they will be using mathematics, but it will be a physicist's point of view, not a mathematician's. Okay, so they are there, and so what do we talk when we talk about points? So in general, points are something elementary, and so it must be something which is small, but this may be misleading, because if you are simulating the evolution of the universe, a point will be even a cluster of galaxies. Something so big that the one end will not know the other end of the point. So there is it's something which is elementary. It's something that we can follow. It's probably something which has no part, but more than it has no part, something that we are not interested in what's inside. Okay, then, before relativity, points were something concerned purely with space, which was an absolute entity, and things, objects, bodies, were occupying a set of points. But every point was very small. I think, for example, the Zeno paradox, no, that is showing that there are lots of points, and they are as small as possible. I didn't study in later year Pythagoras. I'm toying with the idea of writing something about this, and I would like to study Pythagoras because he had a concept of points which was very different. But I don't know. And if you know something, I'd be happy to know it. And then what is dynamics? Dynamics is how things move in this space of points. So object, an elementary point or a particle is somewhere and it moves. And so this is dynamics. Now, with special relativity, we have a first drastic change. Points become events, and space and time are fused into a single entity. So before, there was no need of that. So there was one point and another point, and they would move parallel to each other. And so you could define a point, and then you could define a time, a point in time, which has a different name, of course, it's called an instant. And the two things were not mixing. With Einstein, these things change, and then you go into a single entity which is called space-time, because it's not absolute. Simultaneity is not there anymore, and so we have space-time, and there are two aspects. And if you go to general relativity, so if you put gravity in it, this geometrical thing curves. Now we'll have to see, curving has to do with relations between points. So one point and the nearby one, and they are curved. So in reality, when we talk about points, we talk more about relations between points than single point. Okay, now there are two aspects I want to stress here. General relativity is not a theory which uses geometry, is geometry. So the interaction between objects is due to the geometry of space-time. Gravity is the geometry of space-time. Other theories may use geometry. Everything, if you have a particle which moves on a sphere, you will use geometry. But the dynamical variables in general relativity are the geometry. And the points of this geometry are all possible events. So the point becomes the event, something which happens somewhere. Now, potentially, but there should be some structure. There must be, there is a rod, a clock, or something. So points in general relativity are the set of possible events, and an event means that there is, I wouldn't go as far as quality of consciousness, and this would lead to a more complicated way, but it's, but there must be the potentiality of measuring something. And but they can be as small as you want, technically. In general relativity, you can imagine a rod and a clock as small as needed, ideally. And now, this whole thing goes completely, changes dramatically when you go into, when you insert quantum mechanics. Now, quantum mechanics and general relativity are both products of the beginning of the last century. Some of the peoples were also the same. Einstein gave contribution to both, but they had a parallel development. In fact, at some point people began into different camps historically. But before getting to quantum mechanics, let me backtrack a little bit into mechanics, because I want to show what the difference is. Because we have another set of points. The inverted comma should end immediately after point. And let me go back to the beginning for us. Is that if Newton himself, he realized that if you want to describe the motion of particles, now, Newton was a smart guy, because what he realized is not that things fall. People knew that things were falling. But he saw an apple falling from the tree, and he said, that's why the moon goes around the Earth. So the fact that there is the same force at work. But in order to understand this, he understood that you needed to know a set of forces and a position and an initial velocity. In fact, the Earth goes around, the moon, the Earth goes around the sun, because it's falling on the sun, but at the same time it's moving around the sun, and so it goes on an elliptic orbit. So you need to know also the position of points, of objects, and also the initial velocity. And therefore, a point is a point in an enlarged space where you put together positions, and we call momenta, is velocity by mass for the technical reason. So this is at the beginning of dynamics, and in order to describe these ideas, he needed to develop differential calculus. So Leibniz had done it more or less at the same time, but he put the things together, and because now this is relations between points. Derivatives is our move, so it's points and what happens infinitesimally nearby. Now this is a little parenthesis. He delayed for 1 year or probably more the publications of Principia, because he knew, he had calculated the motion of a point particle around a bigger force, but he wasn't sure, he had this problem that the planet was too big, was not a point. So he had to work some mathematics to convince himself that he could really approximate a planet with a point, which is what we do when we solve in our second or third, first year at the university, the motion of a planet, we consider it to be a point. And so again, this is the first example in which a point was a very extended object, a very big object. And okay, so now in physics we call it the phase space. So the syntaxis is a bit, I wrote this sentence too many times, and there is some, sorry, the first sentence, I'll say it again. He identified a point as in a larger space, as I said, in which you have position and velocities together, and the state of, so this is the state of motion of a particle, where the particle is and where it's going. And it's important, of course, that there have been Descartes, so that he could give names to the points. So he wasn't using necessarily Cartesian coordinates, but this is another non-trivial step, the fact that you can give names to the points. I'm not sure, but this can be the first time that higher dimensional, more than 3, are introduced in physics. Because geometry, of course, was there, and was mostly plain geometry because people had to measure fields, and after the Nile River inundations, they had to reconstruct the properties. But I think certainly at this point people were talking of spaces of 6 dimensions, a particle in 3 dimensions and the velocity, so at 3 dimensions. I'm not sure if in mathematics this is the beginning. So he has this state of motion of a point, and he introduces differential calculus. So he gives structure to the Euclidean, this Cartesian space, and the structure is relations between points. How you move from one point to another, and it's the infinitesimal relation. So it's not Pythagorean, it's really moves a little bit. Now, and this is, since you are the philosopher, I am not clear how these points that are used connect with Leibniz monads and even before Giordano Bruno monads. I'm very keen on Giordano Bruno because he was from our university, and we are celebrating the 1,000 years of our university in 6 years, so we are doing lots of things about history. So I'm now studying Giordano Bruno, trying to understand it, because he also was the first cosmologist here. He has, unfortunately, Giordano Bruno is remembered as somebody that was burned by the Inquisition, which was very important for him personally, but he was an heretic. But everybody thinks of Giordano Bruno as an heretic, but it's okay. But then he said some very interesting and not very heretical things now, because he understood that the cosmos could evolve, so there were things. So this is my next cultural project is to study Bruno for the celebration of 1,000 years in our university. Okay, then after Newton, Lagrange, Laplace, Hamilton, many more understood various aspects of dynamics, is what is classical mechanics, which is the geometry of this space. Now, because the geometry is not so simple, it's not only free particles moving around in forces. Particles may be forced to be on a surface, and the surface may be curved, so there will be constraints. Anyways, this, and then things like Hamiltonian. If you have a gas, a system is very complicated. It may take, to describe the motion of the state of a gas, you will need to know what every particle, every molecule is doing, and in a mole of gas is 10 to the 23 objects, 6 times 10 to the 23 times 2 is not, the 2 is not what is worrying us. But it was two things were realized. One is that, of course, knowing all this information has no operational meaning. Even now we know that the information, in order to store this information, it would be impossible to store this information. The universe is not big enough to have all the information. And the other point was it's not really relevant, because all you want to know is that there are so many points nearby which are basically indistinguishable if you are looked from afar, that you need very few numbers, temperature, pressure, volume, because all of the other ones. However, in classical mechanics, and this is important even if you talk of temperature and pressure, the state of a gas is one of these points in this huge space. Then all of the near ones are they cannot be distinguished by us, but it is one of those in classical mechanics. It's one number of this. And now, for system with all few particles, it may be possible to know the position of a particle, because whatever measurement we do, there will be some experimental error. If you are measuring where something, I'm talking of classical, but there will be, you measure with some rod, with some clock, or whatever you do. There are experimental errors. And so one can have a probability density. In physics, this is what happens really. You don't know the state of a system, but you know with some error, which is a bell-shaped, usually it's a Gaussian, it's a bell-shaped curve, you know that more or less the real value is there. Now, this is a limitation due to technology. So in principle, you can make it smaller and smaller, this bell-shaped probability density, and therefore, because in reality, there is a point in phase space. A system is described by a point in phase in classical mechanics. Then the fact that I don't have metallurgy able to do a very tiny slits on a rod to distinguish the distance between 2 points, it's a physical problem, it's not a conceptual problem. So technically you can make the Gaussian very small. There is another thing which I will not discuss because it was known to Poincaré at least even before, is there can be, however, the difference if you have two initial data, say initial position, if they are they can be very close by, but if the system has some forces of a certain kind, after a while they may go wildly different. So there is systems which are chaotic. Chaotic system is that when two very initial conditions then bring you to completely different trajectories. But classically, if you knew with absolute precision something, and it's possible to know, there is reality in a point being somewhere. Okay, we may not know because we are limited, but the Lord will know, is there. Now, this is changed dramatically because there are two fundamental quantities. One is slightly older than the other one. Now, I'm talking of dimensional numbers. Speed of light and Planck's constant are dimensionful quantity. They are different from pi or the Napier's constant, which are mathematical constants. So the Lord had very little choice in the choice of pi, but he had a lot of choice in the choice of C. In fact, there are books, Mr. Tompkins, which shows how the world would be if the speed of light, instead of being 300,000 kilometers per second, was 30 kilometers per second. So you move and things change color because of Doppler effect and so on. So these two things together change, and experiments of course, change our vision. Now H has dimensions of an area in phase space. There are three fundamental dimensions, which are length, time, and mass. and h has dimensions of an area in this phase space. No? Phase space is position times velocity, which is length divided by time, times mass, which is important. Now I will not go. So the area, this is a constant which has the dimensions of an area in phase space. And this defines a minimal area in phase space. Minimal area in phase space, not in the sense of a discrete area, because this area you can squeeze, but it's the minimal area that you can measure. You cannot know the position of a particle more than this minimal area. And I will justify this with something which is called the Heisenberg microscope. I'm talking of the Heisenberg indetermination principle. And I will use the fact that light is made of quanta, and this is due also to the presence of the other constant, and was discovered basically by Einstein. And I will make this experiment. So how does this work? Up there, delta x, delta p larger than h bar. Now delta x is in one dimension, how the indetermination of the position of an object. Delta p is the indetermination of the momentum, therefore of the velocity of the particle. And there are numbers which are delta x. I know that a particle is somewhere with an indetermination of some centimeters, millimeters, nanometers, or it has a speed, let's say. Mass doesn't play a role in this discussion. It has a speed which is whatever, millimeters per second, centimeters, kilometers, parsecs per second, with a certain something will be more or less this. And you know that the product of the two must be larger than this h bar. And it's important that h bar has dimensions. And how does it work? This is something due to Heisenberg. In order to know that something is somewhere, I should shine some light on it, because that's how we know. It can be another radiation, can be a neutrino, but I should shine some light on it. And then I should capture the light which is deflected. So I have a big microscope, and I shine some light on some part of space where I suppose there will be something. If the light is scattered, does exactly this, I will see it in the microscope. Now light is made of quanta, so light has a wavelength, and it's made of quanta which fix the wavelength with the energy. So, of course, if I send a light which has a large wavelength, I know that somewhere is there because it has scattered, but I don't know where in this wave. So I need to have a particle of light, a photon is called, which is small. But because of relativity, if it's small, then it's very energetic. So what happens is that I send this very energetic object to the electron, then I see that it has scattered, so I knew that it's somewhere there was this object, but this was very energetic, so it gave it a kick, and I don't know which speed it will have afterwards, assuming it was at rest or it was moving, how much is the exchange of speed. So if I put the two things together, and I do the calculations, it's done this in the third year, and you do the calculation, you end up with this formula. Okay, I'm increasing my Einstein grade, I think formula. Now there will be a few formulas. Is what I say in words. This slide is what I said in words. I want to just show, but the important thing is this one. You do the calculation with a microscope, and you find a certain formula. Then you do the calculation with the theory of quantum mechanics. Operators on an Hilbert space, I mean the real thing. And you find a slightly different number. In principle, the principle is the same, but instead of finding h, you find h bar, which is h divided by 2 pi, divided by 2. So there is a factor of 4 pi. So the principle is the same, but the heuristic way gives you an order of magnitude, within an order of magnitude the right answer. Now, I will not affirm that quantum mechanics is well understood. I have been teaching a class in quantum mechanics for 25 years, and I can tell you for sure that no one understands it. Feynman said if someone is telling that he understands quantum mechanics, he's lying. However, I can teach it and be paid for it. And it has a solid mathematical framework. And the solid mathematical framework is better than the physical interpretation. And so Weil, Wigner, von Neumann, the one that talk of pointless mathematics, and other people like Van Nijmegen, Moser, Kohn, not Moser, should be Siegel. I don't know why I confuse always Moser and Siegel. Anyways, now I will don't want to be technical, but this is the static of noncommutative geometry. For ordinary geometry, topology, relation, all the information relative to points and their relations, how they are close to each other, can be encoded in the functions defined on this spacetime. A physicist would say the fields. A field is at each point in space gives a number, and there are lots of fields. So instead of considering all of the points, I consider all of the fields, all of the possible fields, and functions are usually commutative. So the function on space is in this room. You take a function like temperature, and another one which is the speed of I don't know, the various functions. You can think of various functions or coordinates. Function x is a coordinate. Log of x, x squared, exponential. There are other functions, and they commute. If you multiply x by x squared, you get x cubed, and if you do it in reverse, you get x cubed anyways. So this is commutative. Now, in the formulae for quantum mechanics, the functions are not commutative anymore. If you multiply them in one order, it's not the same as multiplying them in another order. I can give you an example of a non-commutative thing, which is mundane, is rotations. If I take this telephone and I rotate first towards that wall, and then towards that wall, I end up with this. So I do two operations in order. First is this one, and then this one, and like that. Now, if I do first in that direction, and then in that direction, I end up with a different. So rotations are an example of non-commutativity. But coordinates are commutative. If I move this one, translations are commutative. If I move this way, and then this way, or I move this way and then this way, I end up in this place. Anyways, well, in phase space, this is not true anymore. There is a non-commutativity between position and momentum. And if you do the framework of mathematics that is done, you don't need to do very high up, but starting Hilbert spaces, etc., you find this, they are operators, you find a complete mathematical things, and you do calculation. You can calculate the spectrum, the emissions of atoms, and lots of things. And however, even in quantum mechanics, the problem is between x and p, is not between x and x. So, in fact, as I say, x and y, they commute. Okay, now things change if you put relativity in it, because I will introduce a third fundamental quantity, which is the strength of interaction, of gravitational interaction, this Newton's constant. Now I have three constants, and I'm putting them together in a clever way. I can have a length. So the other way around. Each constant is kilometers by seconds, and but by putting them together, I end up with a fundamental length. And this fundamental length is Planck length, and it's very small. It's 10 to the minus 33 centimeters. But now at this length, quantum mechanics, relativity, and gravity, so general relativity, They are all important. So this is the scale of quantum gravity. Now, there is a phenomenon which was noted, say probably for the first time by Bronstein in 1938, but it's presented independently in a more modern and terse way by Doppler, Fedele, and Roberts in 1994. And I was discussing this with Brandon. Bronstein was a physicist in the Soviet Union, and he was taken by the Stalin police immediately after he had written this paper, and was actually shot at that moment, and the family wasn't told about this for several years, and this is a bit of sociological thing. So he wasn't there to somehow push his own ideas, and the world was completely forgotten. Then it was rediscovered, and someone noticed it. And I will say this in a very heuristic way. So I will do again the Heisenberg microscope, and I don't care about velocity. I just want to know if something is there. The key will. I don't care. I want to know if something is there. So I'm interested only in space. So I have to take I can take a photon which is as energetic as I want. I don't care. So I take it more and more energetic, and I have to concentrate this photon in a very small area, in a very small volume somewhere. I'm looking for a point. Now, if I put gravity together, if I put too much energy, it's like putting too much mass into a small volume, then I create a black hole. It will be a microscopic black hole, not the ones that you see in movies, but it's a microscopic black hole, but a black hole has a volume, and it has a horizon, and whatever is inside the horizon cannot communicate with the outside. And the volume is the Planck length cubed, of course. Not of course, but you do the calculation and you find heuristically this. So I am at the microscopic, Heisenberg microscope case, and I would now have to do it in the proper way, which I didn't do, but which I can do in a class in quantum mechanics. So I will have to do it with the proper mathematical framework that does everything with a theory, well-established theory like quantum mechanics. And I cannot do it, because we don't have a theory of quantum gravity. A theory of quantum gravity. So, we don't have a quantum gravity theory, but if you talk with my colleagues, several will say that the most serious candidate for such a theory is ... And different colleagues of mine will fill the ... with different answers, of course. This means that we don't have a theory. Again, I go to Wikipedia, I cannot never think of something higher than that. It has 25 approaches, and there are 23 are in other approaches, and 2 are given the sub, say there is quantum gravity, then there is string theory, loop quantum gravity, then there is other approaches, and there is a list of other 23 things. In fact, one of the 23 is also noncommutative geometry, but then it links to applications to the standard model, which is not really a theory of quantum gravity. But anyways, Wikipedia is it's like every religion has to be interpreted with with something. So but this just shows you that I must say that for physics and mathematics, if you don't go close to things like applications, especially for mathematics, Wikipedia is quite good. I use it a lot because I never remember the definition of a ring, an algebra, division algebra, something, and then I always go on Wikipedia and it gets me. And also for theoretical physics is okay. If you get close to controversial things, then one has to be more careful. So I tease Wikipedia, but I actually use it and I give them a little bit of money every time because I feel guilty that I use too much. Okay, in generality, space-time becomes not only curved. I have spoken for about half an hour.
A little bit more, but yeah.
I spoke for more than half an hour.
Yeah.
Okay, I will condensate things.
As long as you don't go over an hour, it's fine.
Okay, no, I will, the number of Einstein increases a little bit, but also the speed, to show you that I do actual calculations. In general, it becomes not only curved, it also becomes dynamical, but you have this problem, which is the problem of renormalization. You have that, you have infinities. It's like taking the limit of r going to 0 of the quantity 1 divided by r. So it grows and it cannot be defined, becomes infinity. However, there is a procedure which is called renormalization, which somehow subtracts infinity in a very controlled way and works very well. Although mathematically it's a bit iffy, but in this ultraviolet divergence, because they are short distance problems, they become, they don't pose problems for the concept of point, however, because fields are defined on a regular flat space-time, and you can do calculations, and they are very successful. There are some calculations done with renormalization which make predictions of quantities related to electrons with 14 digits. And then people at accelerators, the prediction is an infinity of digits, but the experiment verifies this with 14 significant digits. So it works. It works, but we know that it's not going to work when gravity is important. However, the scale is very high. Now, the Large Hadron Collider sees things at the order of 10 to minus 20 meters. This is 15 orders of magnitude, 1 and 15 zeros, away from the Planck length. So we are in experiments far from quantum gravity, and in energies means that we are at 10 to the 4 GeV, so that we are far. Even LHC is far from quantum gravity. Problem is that renormalization doesn't work. I will skip this slide because it's somehow technical, but it doesn't work. So you try to use the theory that we have for this quantum of gravitational energy, and the formula don't make any sense. You don't have a predictive power. So, and this is the last part of my talk. There is the need for some sort of quantum space-time. So now I'm quantizing points. And what is the mathematical structures? Now, this is underway. And one possibility is to do again what was done for quantum mechanics. So say that in the small coordinates don't commute with each other. So it's not true that if I do this and this, I end up in the same place, except that the difference will be so small that no experiment will ever see it macroscopically. But the structure of space-time so it emerged in this approach emerged in some limit of string theory, and there was a famous paper of Seiberg and Witten, and it was very fashionable for some time. In fact, some people confuse noncommutative geometry with this. It's not. This is an example, and it has to do. Okay, this is. I was having a discussion with Nick for some time. If I have the fields which don't commute, is the point still there or not? In my opinion, there is not, because operationally they are not. I cannot measure them. They can be a mathematical device, but physically they are not there. And in fact, in noncommutative geometry, it's a pointless physics. I describe things with fields, I describe things with a mathematics which does not need points, actually cannot have points because of this non-commutativity. Okay, so space-time is not anymore made of points, and the relations are between operators, one would say mathematically, but between distributions of points. I cannot measure a point exactly. And Okay, I like the fact that I say you need a machine in the ghost. So if you are measuring something, so if you are the ghost, but you need a machine to do that. If you want to do points, and this will be fields, this will be physical entities, and we know, although we don't know what will really work, we know that what we have will not allow you to have points. Okay, there was another part which I knew I wasn't getting to. Let me see. Okay, no, this is it. In string theory, space-time is quantized because the coordinates are fields on the two-dimensional surface. A string is something which is not a line, no? So it's a two-dimensional. And so you have fields in this two-dimensional. The word is like fields are usually defined in 3 dimensions: temperature, velocity. But there is this 2 dimension, which is the surface of the strings, and the number of coordinates are the coordinates are the fields there. Problem is that there are too many of them. To make sense, you need 10, and you have to curl them. Look, quantum gravity becomes a form of spin relations, but all these are non-commutative geometries. Really, I will not discuss this in detail. But let me say that the geometry is inspired by Heisenberg matrix mechanics. So instead of having functions which are valued in points, you have matrices. Now matrices have this characteristic: if you multiply 2 matrices, you make a row by column algorithm. If you multiply them in one order, it's not the same as the other order. So instead of having numbers, you have matrices, and this was Heisenberg and Hilbert independently. And everything is described by spectra of operators. And there is this construction which is applying to space-time what happened to quantum mechanics, but not in an immediate way. It's not necessarily X doesn't commute with Y. You have to take into account all of the symmetries of the symmetries are very important, the rotations, etc. So I will not discuss this. I will just want to show you one picture. This picture is very important because this is the strength of the interaction, and is the way with which we can study things which are at the... Now, you know there are 3 fundamental interactions, 4 with gravity, but without gravity we have strong force, weak force, and electromagnetic force. The strength, this is the strong, this is the weak, and this is the electromagnetic, and this is how they change with energy. These forces change with energy. So we can infer what happens to high energy by studying how the forces change. And so we don't need to be, LHC is here, is 10 to the 4, is here. Something happens here, in fact you see that something is going to happen. But so you don't need to make experiments here, it wouldn't be possible. But if you make good experiments down there, then you can infer what's happening. But then you have to also make these mathematical things I was saying. The theory doesn't work together, so you have to regularize theories. To regularize, to make some technical things to avoid these bad infinities. And this is done by cutting to energies. I will not describe things. This I will just go to the conclusions, but seeing this. I'm sorry, no, I have to say the punchline. This, if you make this cut off, so if you want energies to be below something and you do the calculations regularizing, you find one curious phenomenon. In general, points talk with the fields. Okay, so they exchange fields, and so you have, for example, if you are in a gravitational force, the force here will be, if the sun is there, the force here will be stronger than if the force is here. If the weak force will be somehow, the strong force the other way around. The closest you are, the less the force is, and so on. But so you have the fields talk with each other by exchanging fields. The points talk to each other by exchanging fields. If you do this many of these quantum gravity things, the correlations between fields disappears. So points don't talk with each other. So that you cannot go beyond a certain level, because at that point points are not related to each other. So you have a little volume of points which are not related, so the volume is all the same to you. And and this is common in very ways. Sorry, go the way around, and I'm finishing. So points may be there, but they are non-operationally visible. You cannot really measure them. In whichever way, we don't have a good theory, but all the theories point in the same direction. And I think that there is something like a phase transition. So we have a normal space which is made of points, but this is true if I look from far away. It's like high temperature, or you have the phase that we have, the phase of space-time is the one made of points. But then if you are at high energy close, you have like a phase transition. Phase transition is that if you have water, you describe water in a certain way, the molecules moving and friction, viscosity in a certain way. If you have a phase transition, the relation between the molecules of water just disappears. They are not tied to each other because they are a gas. Gas is still the same molecules of water, but it's in a different phase. So I see things in this way. I see that there is a phase which is the long distance phase, which is the one in which we live. But then there is a phase in which there is no, phase in which we are is like the liquid phase. Points are related and they exchange fields. Then there is another phase, and in which the points lose connection with each other. And everything is, so the way this is like a deep water fish trying to understand what goes on above his ceiling. Now the level here is like the energy, or the short distance. So you look up, they know that there is something beyond there. They know that if they are near vent and there are bubbles going up, so you know that there is some sort of theory, but they don't really know they don't really know what is there. They cannot really understand it, so they need to do something, and this would be the experiment. I don't think they will have to do some theoretical thing in which we have a theory which makes us jump and see what is this the thing which becomes a gas. And that with this jumping fishes I will finish at least. Okay.
Thank you.
I ran a little bit on the final. No, but it was intentional. I wanted to. I knew, but I wanted to give force to the fact that we are doing actual calculations. I mean, we are so while we don't have a quantum gravity theory, several people are at least trying to do it.
Right.
Okay. There are questions.
Thanks. So I just wanted to hear more about the claim that you made on your second to last slide that high energy points are uncorrelated. So
yeah.
You say something about what that where that result comes from.
Okay, what it comes from is this. In order to describe, let me phrase it in a low Einstein grade. In order to describe geometry in non-commutative geometry, as I say, your space becomes non-commutative. Although I don't know what sort of precise non-commutativity it is, it would be some matrix mechanics.
Sure.
Now the infinity comes from the fact that those matrices are actually infinite matrices. So when you multiply two, you take an infinite matrix and made of finite numbers, and another infinite matrix which is made of finite number. When you do the multiplication, you have to sum an infinite set of numbers, and then you will get infinities coming up. So you have to impose some cutoff in energy, because the large matrices is because energy can go to infinity, or distances go to zero. The two things are dual. So you have to make to put a cutoff. So your fields will be matrices because they are non-commutative, but in order to make things, to have things sense, you have this theory with a cutoff. So your formula, your calculations are done with this cutoff. And this cutoff has a physical meaning, is the surface of water. It's a scale. Okay, when you do renormalization, you can have a cutoff that you send to infinity, but in this case, you do have a cutoff which is physical, is this Planck length. Same way as you can do a length, you can do an energy, you can do a surface, you can do all the quantities that you have. So you put a cutoff in all your matrices, which is not really taking the matrix to be finite, but you force the matrices to go to zero at infinity, so that when you do these multiplications, your series will still be convergent. But then, at this point, you see what is the behavior of the propagation of fields at short distances. And you find that this goes to zero.
Okay, I mean, so from what you just said, I could just be thinking here of ordinary quantum mechanics, L2 functions. I've got my infinite matrices, but the operators are well behaved because they're defined on this restricted class of functions. What more is going on to understand?
If you want really technically.
Yeah, you can go up at least one or two more Einsteins.
I can have yes, now fields are bounded operators on an Hilbert space, but the action of the theory is with a cutoff functions at a certain scale. It's called the spectral action. So the fields are still acting on an Hilbert space, but the cutoff is inserted in the action. So when I take the action, which is the fluctuations of these fields, I take only fluctuations which go to zero at infinity, or they have a sharp cutoff.
So this is a cutoff in something like energy?
It's a cutoff in energy, yes. But I insert it in the action, not really in the fields.
I see.
Okay? So actually, if you look at the slides, there are several references, and I have just written. Actually, probably it's not there. There is a book that I wrote with other people. Julius Vess is one of them, in which I describe the mathematics. And then for physical applications, I just wrote a review. If you look on, Inspire or the archive, and the book, is a Springer book, but it's available for free. I think I don't get any money anyway, so it's available. I think Springer has released, and they wasn't selling it anyway, so he sold it enough. And then the other one is called Strings, non-commutative geometry, standard model, and all that.
That's the review.
That's the review. And there are a few reviews. If you see something with several of the papers with only my name are often reviews. This is not with the PhD thesis of my two students, but the review and things like that, I take full responsibility. Usually other papers are with students or the collaborators.
There's also there's the paper, I guess, from a talk you gave, the points lack there on,
yes.
on the archive.
Yeah.
But also sketches this.
Actually, this was in a meeting with physicists and philosophers. So this has a phase transition. First half is similar to what I was saying, and the second half is for physicists, and it's exactly this.
But it spells it out a little bit more.
Yeah, no. It's Yes, that had an Einstein phase transition. There was the second part I do actually the field theory in the proper, hope the proper way. But
Thanks.
Can I follow up on that?
yeah,
Can you just say what's the sense in which, you know, in commutative geometry that the points are correlated? Because I mean, if they're space-like to
Yeah.
each other, they needn't be correlated anyway.
no, that they can communicate with the field. If you put a scalar field, the scalar field is defined here and here. And I think I have there is something which is called the propagator.
Yeah.
So that if I have a free field, so the function, the fields are solutions of differential equations. Is that exactly the same as in Newtonian mechanics? In Newtonian mechanics, you have a point particle and a set of forces, and you know how it moves. In field theory, it's morally the same. It's an infinite number of dimensions, but you have a field. Field is defined all over space, and space is made of point. And the field, we say, propagates. This field will be solution of certain equations. Also free equation, and there are the straight motion on rectilinear uniform motion. So the field will be there. So solution of a free equation. So if you know the fields on a surface, you know everywhere, because it has to be solution of certain equations. So the points are correlated by the fields. Now, if you take if you have the solution, the equations that you have, if you are in a gravitational field, you know that the correlation goes 1 divided by r squared. Otherwise, they will communicate with a plane wave. So you can know distances and everything, but you communicate with fields. If the fields are solutions of a differential equations which has gravity into it, and these cutoffs which I was saying, at long distances nothing changes, but at short distances it doesn't propagate to nearby things, because it's non-commutative. It's difficult to explain. It's impossible to visualize, because we visualize having the points and the correlation between the points, but you have to abandon that. You have the fields and they correlate, and the fields, from the fields you get the points. Now you are very close by, then you still have the fields, they don't commute, and you cannot get the points if not in an approximate way. And if you insist on getting the points, you get these points, but they are mute to each other, because you are insisting, you are describing things not in the proper way, because you are insisting on using the points in.
So there's long-range propagation, but no short-range propagation.
Exactly.
You've got to kind of give up in
yeah,
thinking that it's propagating.
So this point and this point are long, okay, that everything is fine. But this point and this point are too close.
But it's not propagating.
It doesn't propagate.
It's not propagating through the intermediate points to get from here to here
yes,
somehow.
Yes.
Yeah. Okay.
So no one else has a question.
I'll stay here for another day or two. So in case at some point people want to leave, I will be happy to discuss individually with whoever wants to tell me something. Please.
Yeah, no, we'll take you up on that. But I just wanted to hear more on your answer to Nick. So the thought there is that the commutator between whatever operators are attaching to the fields, there's some way of associating those, at least at long distance, determinately with collections of points. So relative to here, I know what it is to associate an operator with some points over
there
here.
There is a simple example which may be misleading, but in this case will be okay. If you are on a lattice, so if you have a set of points, and they are really one separated from the other. But now if you are at long distance, and the step in this lattice is very small, everything is like this continuous. Okay, so given points you can use, and in fact this is what we do in solid state physics. If you have a crystal, phone unstable propagates. It's the crystal is like a continuous thing because you are in a long thing. The current in this wire is a crystal, but we just consider it continuous. But then now if you go to a smaller thing, you see that the particles are at some distance, so there is nothing between the two things. So this is one way to see it, in which at long distances you have points, but at short distance you don't. So the fields are well defined at long distances, are well correlated, but they are not. But in reality, it's again, it's like the Moyal product. You define the fields is the interaction, which is with a cutoff. So that's it's really the non-commutativity, and the cutoff comes in the interaction.
So I guess maybe the question I wanted to answer to is, can you write down some operators, the commutator of which sort of measures the degree to which they're well defined? So spatially, they're close together. The commutator is large.
Okay, this
very small.
no, it doesn't work this way because the commutator between take something that we know it works, which is quantum mechanics. The commutator between position and momentum is small. So if you are at higher energy, at higher distances, the commutator is like it's being zero, because h is a small thing. So it's a little bit the same thing. But it's not so much the commutator as the fact that these matrices are different from a normal commutative matrix. They are on a matrix.
So it'd be more like raising the expectation value for momentum.
Yes.
Yeah.
Yes.
I just want to ask a simple question, Nick. Professor Lizzi, I was a little confused by your answer to Nick. I was under the impression that you were doing quantum field theory on non-commutative spacetimes. But your answer to him about the fields being solutions of certain differential equations,
Yes.
sounds like you might be doing classical field theory on non-commutative spacetime. Is that what you're doing?
Okay, I do several things, and so let me now separate things. I've been guilty of doing several crimes. One of them is to do quantum field theory of non-commutative spaces, and this is one thing, and then there's the discussion. The latest things which I was saying, which is my pet theory at the moment, is the non-commutativity. It comes because I look at spectral operators. So everything is operators. The fields are the normal fields, but since I look at them as spectral things, and then I put this cutoff, they become non-commutative because of this cutoff. So I'm doing, and I don't have space-time. I only have the fields.
Right.
And space-time is
It's an emerging thing.
It's an emergent thing.
Right, and what emerges as a non-computer space-time.
What emerges is that there is no space-time.
Right. Well, I mean, what we were.
There is space-time only in long distance.
That's all I mean by that.
But not in short distance.
Exactly. That's right.
So the emergent space-time is.
So that emergent space-time is really out of a classical theory in this particular case.
Well, quantum field theory, because I do quantize it.
You do quantize. But I mean, do you need the quantization in order to see the emergence?
I need the quantization, absolutely.
Do you need the quantization in order to see the emergence?
Yes, because the action which I write is the equation, the theory which I use is based on Feynman path integral, is a quantum field theory.
So you would not get the effect that you're talking about without actually using the method?
No, without path integral I wouldn't see.
So that's essential in order to get
It's
the
essential.
effect.
Yes.
Okay.
It must be quantum field theory.
So
there is H pi. I need all of the constants, and I need all of the techniques which I know from quantum field theory.
Would a classical fields, which exhibit based on the same operator algebra as them, classical fields without the path integral, would they also need regularization in the same way? Because you're still going to have your information.
Yes. No, you wouldn't need the regularization because you will have only a classical field propagating, and you wouldn't sum over all the possible.
So you wouldn't test out those regions of field space which are causing the problems
because in fact, this is what happens is that since at large distances, the fields become classical because the sum over all, the path integral sum. But you told me two Einsteins, and then now the questions are at least four. But so at large distances, the path integral is picked over the classical solution. So at large distances, I won't see anything. At small distances, where the fluctuations count, that I put the cutoff.
Sure.
Because otherwise I get infinity. I put the cutoff, and then the points become
Right, but the infinite matrices, or the fields are still true even at large distances, even at large scales.
Yes.
Okay, but just they're not problematic because they're just following the classical.
They are not operationally valid at small distances.
That's right, yeah.
Because
So you're
classical mechanics. Now this is is an interesting discussion. Is classical mechanics a consistent theory? So if you have a forget about the fundamental constants, or take only a few of them, or take only C.
Right.
Is this a consistent theory? This is something I wouldn't be sure about the answer. Because then, if you have really a completely classical theory, some effects like this Poincaré sensibility of initial conditions, etc., become suddenly predominant. And so I don't know.
It also might depend on the classical theory you're talking about.
Definitely.
Right.
No,
it could be that classical electromagnetism isn't in classical mechanics.
Absolutely.
Right?
Absolutely.
So,
Absolutely.
just like in quantum mechanics, it depends on which theory.
Yes, absolutely. So,
But these are classical theories in the non-commutative space.
No, I think you're just talking about classical theories, classical theories.
no, classical theory, classical theory.
Not non-computer space. Just ordinary
Yeah.
classical theories.
Yes.
We don't know about their consistency.
Yes.
Right, absolutely.
Okay, it's always a difficult thing, because what does it mean that a theory is consistent for a physicist? There is always, you need to have an operational measurement you have to do things. Otherwise, consistently, mathematically consistently, classical mechanics is perfectly consistent mathematically. Mathematical physicists do beautiful things with them, prove beautiful theorems, and I enjoy them. But it's not clear whether they can be somewhere where there is an observer.
Yeah, sure.
Things become. That's why you work, actually, because it's not sufficient to have a theory which has good equations.
But I also just want to make a couple points. So we have to leave. I'm sorry to rush my questions in here, but just want to make a couple points about renormalizability. I mean, renormalizability is certainly a short distance problem. Perturbative renormalizability
Yes.
is certainly a short distance problem. But perturbative renormalizability is, says something about a certain way of calculating within theory. It doesn't say something about the theory necessarily as a whole, right? There's lots of non-perturbatively renormalizable theories that we know about, which are so in other words, they're perturbatively not renormalizable, which are non-perturbatively renormalizable. There's lots of
in the
things.
23 Wikipedia chantings, there is asymptotic safety,
Right, asymptotic safety.
which is a theory which is also predictive, and Weinberg is pushing for it.
Proponent, right,
Yes,
the proponent of it,
but
sure.
there, near the fixed point, in fact, I'm in good discussions with people that do this Bonanno, etc. Their space-time, they're near the fixed point of the flow, is not clear is a normal space-time.
Oh, of course it is, right. But it is asymptotic, it could be asymptotic, it could be. But there's other asymptotically safe theories you know which are perturbably not renormalizable. Sigma models in 2+1 dimensions and all sorts of things that you can do that with. And also, just because a theory is perturbatively renormalizable, like quantum electrodynamics, doesn't mean it's asymptotically safe, right? You got the Landau pole there, and you got some sicknesses that quantum electrodynamics has, even though it's perturbatively renormalizable. And so this the whole question about renormalizable and what it means for the actual statements about short distance behavior. Here, it's very complicated stuff.
Absolutely. But in fact, these 23, 25, 23, they are clearly, all of them, wrong. They probably, whatever, if I hope we'll be alive, but whatever, whenever we will really get hold of things, it will have elements of, probably not all 25, but that I'm convinced. I mean, there will be some point, and then you see, like Einstein, and except that things are getting, time are getting dilated a little bit. Like Feynman with quantum dynamics, Schwinger, Feynman. At some point, somebody gets the right answer, and one says, Schrödinger with Bohr and things. Okay.
In the case of QED, it was Dyson who said the
Yeah.
big figure and find the movie.
Yeah, no, I know. No.
Well, thank you. I apologize for taking your time. You guys could, you have my permission. Professor Lizzi, good. Nice to meet you.
That's,
All four of my grandparents are from Naples. So.
Really?
Yes.
That's not true.
Yeah. Absolutely. All four of them are from Naples. They came to the United States, over 100 years ago, so yeah, it's good to see you.
Okay.
Yeah.
Un compaesano.
Okay, so I have a question that was sent in from somebody who was watching on YouTube.
Oh, okay.
So this is Tushar, who actually we're going to Skype with on Friday morning.
Uh-huh.
I've been talking to him about these issues. I'm going to read the question.
Sure.
to you. I hope it's not
All right.
one Thomas. Oh, well then it's recorded and everybody
Uh-huh.
hears it. So as he said, in classical physics, both coordinates of space-time / phase space and observables are represented by functions. The coordinate functions are in some sense special. Observables like energy are functionals only of the coordinates of phase space.
Mhm.
Consequently, certain universal symmetry properties of the dynamical matter fields of particles can be encoded in a choice of coordinate system.
Mhm.
Okay. That seems like one sense in which it's useful to think about space-time phase-space structure.
Mhm.
In quantum mechanics, the observables are operators on a Hilbert space,
Mhm.
while to the extent that space-time exists on, say, the Schrödinger picture, the coordinates are still functions on the space-time manifold. What is the motivation coming from quantum mechanics of ascribing to the coordinate functions non-commutative behavior rather than just dispensing with the ideology of coordinate functions altogether?
Okay, here is really the Heisenberg versus Schrödinger. In a sense that up to the level of Schrödinger, you can do quantum mechanics, which is the theory of the wave function. So there is this wave function, but then it's the observables which enter the game and become important. So when we talk of all these coordinates and things, but the important bit is that they must be operators because we know we have a measurement theory. We have a theory which says that what we measure is the spectra of some operators. Otherwise, this wave function is not operationally valid. So now I have not made a measurement theory of quantum field theory, which would be a complicated thing. But in general, it is believed, one of the paradigms, that measurements are spectra of operators. And therefore, positions will have to be somehow operators. Now, in noncommutative geometry, the operators become the fields. You still can define some position operators, but then the spectrum will not be the point spectrum of something which can be localized. So I think this is more or less what
so much.
happens.
I have to come back and I get my bag.
Yeah, it blends in so well.
Your Neapolitan beat.
So easy
Your
to
Neapolitan beat. Sure you can.
Okay. Okay, well, I think so. I read that. Maybe there'll be a reply in a second. We can see it two shows. Yeah. So that's the kind of. I mean, I often get this when questions like that when I'm talking about non-commutative geometry, about how. Yeah.
Because the important bit is that really non-commutative geometry is very much in the Heisenberg framework.
So it's motivated by this, it's not required or something?
It's not really required because we are applying it to a different higher level. There is one thing is that I say that quantum mechanics there is a well-defined mathematical structure, but no one seems to understand it. Quantum field theory is bizarre because there isn't a mathematically well-defined thing, but somebody said quantum mechanics is a mystery and quantum field theory is a functor. But there is a precise way to go from quantum mechanics to quantum field theory. in which you just take some, it's called second quantization sometimes. You take some objects and you make them operators on a Hilbert space, which is called the Fock space, and so on. So there is a procedure to go there. And but then you somehow lose the connections with classical physics. It's very difficult, because it seems that we can go in steps. We can go fairly well from classical physics to quantum mechanics to quantum field theory, and probably quantum field theory one day to quantum gravity, but it's not easy to do shortcuts, because the formalisms are incompatible, so you have to get them connecting to each other. This is one of the difficulties of talking of points in quantum field theory. That point is a classical, really a classical object, and so you have to have operational things.
But one thing you might say is that you have coherent states in your quantum field theory.
Yes.
That are strongly peaked around.
Yes, you have the substitutes for in quantum field theory, which is in quantum mechanics really, for the harmonic oscillator. Yes, and in fact, I do lots of things with coherent states in noncommutative geometry, but coherent states are they are unlocalizable. They are the best you can do of something that you cannot localize. But they are just one set of states. So one point of view is that your points is the tip of all the coherent states. No? You can say that. But then coherent states is just one possible set of states. They are not pure states, technically. So there are technicalities of, they are localizable, they are not points. They are the best approximation to points. Whatever you do. This is another problem, look quantum gravity. Look, this spin foam is fantastic, but then it's very difficult to go from this spin foam to classical space-time. You don't get a good limit. The other approaches, in our, when you do quantum noncommutative geometry, there is a noncommutative parameter, you send it to zero, it is a length of infinity, it is an energy, and then you do find something that looks like, in some extent. Look, quantum gravity has this problem, paradoxically. So they know how to do quantum gravity, but they don't know how to do classical gravity, or how to make classical gravity emerge, classical space-time emerge from this. So this is a bit.
Well, I have a clarificatory question about the cutoff that you were talking about. So you said that is the Planck energy, right? But you also said that's something you put in to regularize the energy. So I don't see how you can go from it's just something to renormalize to that actually comes out to the Planck energy.
No, okay. There are two points of view that you can have in renormalization. In Feynman, renormalization is subtraction of infinity. In asymptotic safety, and also my point of view, is that there is something which is a physical scale at which something happens. So you need renormalization. Renormalization is not only the attaining of infinity, it's also how the theory changes with different energies. And so I still have the theory looks different at different energies. And it goes berserk when you get near the cutoff. Because the cutoff has a physical meaning. It's like the temperature. So you are underwater, and okay, if you are a fish at 100 degrees, probably you will regret being there, but you are underwater, and you know that if your temperature increases, viscosity, then lots of things change. And then at some point you start having bubbles. And when there are a few bubbles, you can still describe them. When water is boiling, then you have a phase transition, so you cannot describe this water as you were doing before. You know, what you were describing with the flow, velocity as something, viscosity, pressure. Pressure basically goes to zero as you are doing it. So the cutoff for me, which is either an energy or a large energy or small distances, is the point in which something happens. And in my formula, then I can see that something happens. And this is, from this point of view, what's the name of
Tom?
Tom. What Tom was saying, asymptotic safety is another theory in which there is a phase transition. So the quantum gravity is I think is a phase. You'll have to have quantum space-time, which will not be.
I thought you were maybe asking this, and no, I don't know, but the
Okay.
slightly different way of asking the question. So does this cutoff, does it appear, is it something that it just appears explicitly in the action, or is
Yes,
it something,
yes.
okay, it's not something you just use when you,
No,
when you
write the
normalize,
action.
it's actually in the action.
The action is very simple. Is a trace of a matrix. Now, a trace of a matrix is the sum of the diagonal elements. Okay? But then this matrix fluctuates. It fluctuates because it's like all the possible positions, all the possible fields, all the possible, and the action is somehow the trace of this. Now, a trace is a sum of an infinity of terms, the diagonal terms. And this diverges, this is infinity. You keep on summing numbers, even if these numbers decrease, they can still, if you sum 1, 1/2, 1/3, this is infinity. Then you put a cutoff, and you say, no, my matrices are not really infinite. From now point on, they go to zero, the terms go to zero fast. So this is, but it has a physical meaning in the equation. And you have to put the numbers, and see, we use this also for particle physics, to predict and to discuss the mass of the Higgs and the interaction between particles. And there you know what the number should be, because it's of the order, and then you put the numbers there, and you try to predict the Higgs mass or the neutrino, right-handed neutrino mass and something. So you actually, then this number is from experiment. G, H, they are from experiment. And fortunately they are small, or large, it depends if an energy or a distance, because then we can have classical mechanics, or perhaps if they were, life would be different, or this thing. But because we live in a certain regime, okay, in which we live in meters, seconds, and liters, kilograms, which are far away from the extreme of this